Okay, welcome back. I want to start just by mentioning all of you did the proofs correctly. Um, uh, there's only I just wanted to point out that you have to be pretty careful with how you write the steps. So um, let me just get this out of the way. You can always work on things outside the limit, but once you start putting the limit in, that should carry on. It doesn't disappear halfway. So you can massage. That's the word I use. You can massage the expression however much you want. But once you start talking about limits, because what allows you to, because I think I saw some groups say like, this is the derivative over the derivative. Now that's not correct. When the limit is there, then it's correct, and you can say it's because of L'Hopital. These are small things, but there are also big things as well, because it's good to know how to denote things in a very, very precise mathematical way. So that's why. But it was well done. Right? All of you have the right idea. So today, what I want to focus on is actually something that's quite exciting. It's also quite confusing, but I'm quite confident this class will be able to get it. We will also do a group work that will allow you to really take your time. I'll give you the whole period to do it, where you can really practice and try to understand what is it that this OOB thing actually is. All right. And you will be rewarded when you do the group work, because you will actually find that it does give a pretty good estimation of your test set error. It's amazing. I tried it out last night when I made the group work for you. So we will see. All right. So let me explain first what's going on. So first of all, you need to remember what a bootstrapped version of a tree is. A tree, an ordinary old tree, is just a tree that you make based on whatever training data you give it. So that's, we understand. What's a bootstrap tree? A bootstrap tree is a fake tree. It's where you look at all the data and you take a bootstrap sample of it. Now, a bootstrap sample of something is when it's kind of weird, because you represent all the rows as if they are like balls in a bag with numbers. And you are allowed to take out a ball, look at the number, and put it back. That's why you have it's replace. I keep forgetting that option. Replace equals true in R allows you to replace that thing that you took out. So you could potentially have 2 or 3 times, you might actually see the same thing. You might, all right? And therefore, you make a tree from the new sample that you have made that is actually a resample of itself. So you get a different tree. So you have tree 1, tree 2, tree 3, and until tree capital B. We tend to use that. So today, you have to really differentiate. Capital B stands for how many trees you actually make using this fake bootstrap kind of process. All right, that's capital B. Typically 500. Right? Sometimes 50, depending on, and we talked about this the last time. Now, every tree potentially can give you predictions, right? Now, whether the predictions are good or not, that's what we're trying to assess. So let me start off by explaining. Okay, first of all, tell you what, I will let you copy this down. And actually, this one, I actually got it from my professor at grad school. The textbook does not talk about this, so this is unique. Right? The textbook talks about this, but they don't really describe it very, very carefully. I had a brilliant professor in grad school, absolutely brilliant, right? And he gave very good notes, which I value till this day, right? And so this is from him. Right? He has retired already. Actually, he was so good that his exams were insane, right? So the whole department used to talk about his exams like they were terrible. They're so difficult. He would reserve all the terrible things for the exam. You know, the homework was not easy, but the homework was easier. The exam was terrible. Okay. Really difficult. Oh. So all this notation is from him, but I will explain. All right. Because I wanted to get to the bottom of what a bootstrap out of bag thing and how it's done. So I actually constructed a group work that will really help you implement this. And it's a beautiful idea. It's not that hard if you explain it correctly. All right, I'll try to do my best. All right. And if ever anybody tries to, what's the word, gaslight, right, and tell you that, oh, there's not much math in data science, just tell them to go and sleep, right? Right? Look at how mathy this is. It's not the easiest thing to explain, but I'm confident you will get it. All right. It's because I'll give you some very simple examples that will show you what is actually going on. Looking at this, when I did this, I also did a double take. I had to like read it a few times. And the way I study is if you don't understand something, make a simple example to help you understand it. So that's what I did. All right. That's why I like teaching in this school, because it allows me to actually not just teach, but actually teach you how to learn, which you don't really get at huge lectures and things like that. So, okay, let's look. First of all, last week I did give you the denote F hat star B X as the B's bootstrap tree prediction for X. The random forest predictor would then be 1 over capital B all that. Okay, what? Okay, so there's I think 5 things to talk about. What's X? Someone asked me last week, what's X tilde? That stands for the whole row of data for a particular case. So your age, your sex, your whatever, the X information about the case. All right. What's little b? Little b is one particular bootstrap tree, little b. What's capital B? That's fixed. Capital B is not an index. Capital B, uppercase B, is the total number of trees. So do you understand this statement? It just means, how are predictions made in a random forest? A prediction is made in a random forest by averaging the predictions that every bootstrap tree makes. That's it. You have capital B trees. You find the prediction from every tree, sum it up, and do a simple average. That's how a random forest gets its predictions. And because the trees are all slightly different, you get slightly different predictions, and so you balance the risk out by taking off. Because some trees may be bad, some may be good. That's the whole idea. Now, the whole point about what a random forest is, I don't want to go dwell on that. You can check your notes. Remember, it's when when you split, you don't allow you to check everything. You take a random sample of predictors. That's where the randomness comes in a random forest. A straight up forest, non-random forest, is basically every time you split, you can choose any predictor variables that you want to split on. Random forest tries to take that away and in effect decorrelates the trees. It makes the predictions less dependent on each other. So it's considered a step in the right direction. All right. Now, what is this? Now, okay, now let's get our feet wet into the full definition of what is the method of, okay, what's the goal here? Remember, I told you bootstrapping has a few things. One is to find standard errors. We did a good work for that one. That's nothing to do actually with prediction. You must understand. That's actually to do with looking at trying to analyze the variability of the things that you estimate. That's a variability thing. This one is the second use of bootstrapping, which is it enables you to at least get an idea of what your test error will be. That you must see the big picture. The goal is, without constructing a test set, because we know it's expensive to have a test set, you are sacrificing part of your precious data set, which is left untouched. If you didn't want to do that, could you in some way create little test sets that keep changing, that would allow you to at least get an idea of the performance of your predictions when you do an actual test set? So you must see the big picture is, we don't like making test sets because you sacrifice precious data for that. up to even 30%. That set gets untouched. You can't train on it. You can't do anything. Its only purpose is a test set. This out-of-bag method is a genius way to at least approximate your error on the test set by making multiple test sets randomly as you make trees. Okay, so do you understand what this set IB is? First of all, IB is a subset of 1 to capital N. 1 to capital N means these are the indices of the capital N cases in your data set. Everything. All your N, think of them as people, all the N or houses, if you like. All the possible houses, you index them by 1 to N. This is a subset. And you see, what is this subset? This subset is the indices that did not get included in the B3 or training set, not tree, sorry. You are creating basically random training sets. Remember when you do a bootstrap sample of a sample of data, you are making a fictitious new sample. That's also bootstrap. You take from itself, potentially repeating some rows as well and leaving some rows out. And we already know the probability in the long run of a case being left out of any bootstrap sample is 1 over E. All right, and that's what we asked you to prove in group work 12. So, if for a large enough sample. So, you keep a record for every training set that you bootstrap. Someone's not going to be inside. I mean, it could be that coincidentally, your first bootstrap sample is the sample itself. Could that happen? Yes. But it's highly unlikely. You'll get something slightly different. Someone's going to be left out. Keep a record of the left out cases. That's why it's called out of bag. It didn't enter the bag. So that set stores all those that go. Now, what happens to those? You utilize them as a test set. So you take the beef tree, all right? So you for every bootstrap tree, see, you are summing, if you look at the formula, you are summing over, now the index is little b. You are going from tree to tree, and you are looking at, for any bootstrap tree, go check out that tree's I set. For those indices that did not get included in that tree, predict using that tree on those that were left out. Get those predictions and form a prediction for that left out index. And you do this for every case in your data set. So there's a lot going on here. Chew on it for a bit. Notice there are multiple, there's a little b and there's I. I means I run from every day, no one gets left out. That's why the OOB thing is so good. Everyone gets to play a part to be in a test set. It's kind of like cross-validation, but better. You go from I from 1 to capital N. For every row of your original data set, you ask yourself this, okay, let's say I is 1. I'm in my first row. You go and check as you cycle through all the bootstrap trees from 1 to capital B, which bootstrap tree did not have 1 making it? Then what you do is you predict on that tree for that case, get that prediction, sum it up, and you divide by how many of these predictions you made, like that. So number of indices B such that I is in there. Okay, so let me draw you a picture to help you understand a bit better. Let's just do 3 trees. This is tree number 1. If you want to join it this way. This is tree 1. This is tree 2. This is tree 3. All right. something like slightly different trees. So in this tree, how was it formed? This tree was formed without the participation of case one. Case one did not make it into bootstrap sample. This tree was formed with the participation of case one. It so happened one was included in the bootstrap sample. This tree also was formed with the participation of unit, observational unit row number one. So what this is actually saying is, you need to use this tree to predict for case one. This is bootstrap tree number one, predict on this case, X1. Get a prediction. But are there potentially other trees where one was left out as well? Yes. Find every one of those trees, predict using that left out point from the tree that was constructed without it, and get all those predictions and add them up. And then that division is just, well, how many did you find? If there were 17, you divide by 17 because you're summing 17 predictions. This gives you your precious y hat star, and you notice this is called y hat star 1 capital B. This is fixed. This means this is what this whole sequence of, well, however many, 500 trees is going to predict what the case number one should be. Why does this give you an approximate test error? Because every time you do this, this was not included in the training set that made the trade. That's why I say you are creating random test sets and then cycling through all your trees to get predictions, and you see what you're calculating in the end? You take all, and you might say, how can I know that I will be able to calculate y hat star 1b, y hat star 2b? So here's my question to you. If I did capital B 500, do you think there will be, among all those 500 trees, are there always going to be some trees that did not use a particular point? If I do 500 trees, will there be some trees that did not use number one? Yes. Will there be some trees that did not use number two? Yes. So everyone gets a chance potentially if you do enough trees. If you don't do enough trees, you can't find this. And I'll show you an example. All right. So let's do and then the OOB error rate is this. It's an MSE. You take the original observed YIs because that's your training set. You have that data. You take the original observed is actual minus predicted. This is the mean square error of using this out of bag method. I don't know who first thought of it. It's utterly genius. It's so clever. Everyone takes turns to be in the test set. It's like cross-validation, but even more involved and involving even more computation, which is not a problem nowadays. All right. So let's give you some examples. All right. This should shed light on this. Okay. Now, this is a toy example. Let's say we have 5 cases only. Let me position this. Okay. Let's say we only have 5 cases. Okay? Not thousands of cases, or hundreds. Only 5. And of course, I'm going to number them 1, 2, 3, 4, 5. So let's get some notation in. What's capital N? Anyone? What's capital N here? 5. Good. Okay. We have to keep. Okay. Now, when I say capital B equals 2, how many trees am I going to make? How big is my forest? Only 2. So it's a toy example, but it will help. What's T1 star? Indices that were included in bootstrap sample version of training set. Actually, I shortened it to BTS, which is a huge mega Korean K-pop group, right? BTS, bootstrap training set. I checked out what, okay, so in images, right, they did one dance that was, I didn't know how famous. I checked it on YouTube. It has 2 billion views. right? Just light it up like dynamite or something like that. If I did a YouTube video on bootstrap training set, I'll be lucky to get 25 views. But BTS could stand for that. Right? I'm not even sure what BTS, the K-pop group, what does that? Is it an acronym? What does it stand for? Does anyone know? I never checked actually. Anyway, so bootstrap training set BTS, right? Coincidentally. So bootstrap training set 1 left out. Okay, this is an easy question. Which one got left out? Which observation didn't make it into bootstrap training set 1? 3. Which observation did not make it into BTS 2? Okay, now do you understand why I1? Remember that mysterious I set? Why is I1? I1 stands for which indices were left out from bootstrap tree 1. I2 is which indices were left out of bootstrap tree 2. All right. So we are going to calculate y hat star 1b, y hat star 2b, y hat star 5b. Now here's a kind of a trick question. Is it possible, based on so few trees, to calculate y hat star 1b? All right. Now the answer is this. Was 1 never used at all? No, it was not never used. It was always used. Therefore, it is impossible. This 0 there tells you it never happened that 1 was in a potential OOB test set. So actually the answer is y hat star 1b is undefined here. You can't find it. There are too few trees. If you did more trees, eventually 1 will be left out. Then you could potentially use 1 as a prediction set, to predict on, basically. But here you cannot. In fact, not just 1, 2 was always used. So neither can you ever use 2 to be in a virtual, if you like, test set in this case, because 2 was always used, as was 4. However, 3 and 5 were not used respectively once. Training BTS 1 did not use 3, BTS 2 did not use 5. See? So what happens is this. You then go on to calculate stuff like this. Okay? Y hat star 3b and 5b are the only things that you can calculate. How do you calculate y hat star 3b? Well, there's only one instance where this happened. That's why it's 1/1. You cannot find any other case where 3 was not in the BTS. So you find the prediction that tree number 1 makes for observational unit of case 3. So you see, we are running out of symbols, honestly. F hat star 1 stands for the predicted value for case using tree 1 that was trained on BTS 1, but the X3 means this is for observation number 3. There was only one prediction possible. And so you take that as the definition of what the OOB would say is the prediction for case 3. Do you understand the one for case 5? Because case 5 was left out of BTS 2. So you use tree number 2 to predict for case number 5, and you get a prediction. And then you see what I said? 1, 2, and 4 hat star don't exist anymore. They are undefined, not that they don't exist. You cannot estimate them because you have made too few trees. That's why in the group work which I'll give you, I will ask you to do, there's plenty of time. I want you to make capital B equals 10. You'll see what I mean. Capital B equals 10, so that you will not have this kind of irritating case where one case never got left out. It's too popular. It's in every party. Right? Okay, but this one had too few trees, you can't see it. Now, let me give you another example. In this one, I want you to maybe try to go along with me. Okay, so now let's say, okay, now let's say I added a tree. Same first two trees, but now capital B is 3 because I created another bootstrap sample. The third BTS, who got left out? See, the third BTS is 1 got repeated. 1, 1, 2, 3, 4. Who got left out? 5. Which means, do you see now that 5 has been left out twice? 1 is still left out only once. It's only left out of tree number 1. But 5 now has been left out of tree 2 and tree 3, right? So, can anyone tell me how would I find y cat star 3, 5? Now, I be careful here. How would I make an OOB prediction for observation 5 based on capital B equals to 3 trees? What would I do? Can anyone describe what would you do? You have to add two things and divide by what? Yes, good. You need to divide by 2 because there are 2 indices where 5 did not make it into the training set, into the BTS. Good. What goes on top? Okay, this one's challenging. I'll start you off. It must involve these letters. And the notation is important because it really shows whether you understand what you're doing. I mean, like on exams, I don't care whether you know how to write these things, but you need to understand how to get the OOB predictions. Anyone care to tell me what happens? Okay, I'll give you this. There's a hat here, okay? What do you need to write?
Star 1 and star 3. For each F.
Oh, okay, okay. The stars here. Star 3 is correct, but it's not star 1.
Oh, star 2.
Star 2. Yes. Why? Because only the tree number 2 and the tree 3. Yeah, tree 3 and tree 2 did not have case 5. And notationally, what should we put it here to be very clear to people? Which X is this? 5. You are predicting for case 5 using tree number 2, tree number 3, and these are the bootstrap predictions. And because you have 2 cases slightly different, so this is not something that is easy at first blush, right? I'm trying to make it as plain as possible, but you see, you got it right. I was even wondering whether I got it correct. Okay, it's not. This is something you cannot learn on TikTok. No one's going to teach you this. Right? It's also not. It's also something you should not learn when you're scrolling through TikTok. Right? It's you have to keep track of many things. But is it an appealing concept? Does it make sense? It does. It's genius. You are not sacrificing any part of a training. Your training set becomes your test set, and it's random, which is even more beautiful. Note though, we still don't have enough trees because 1, 2, and 4 never got left out. So we still can't. So that is why I have actually constructed a quite a lengthy group work, which I will now let you start. And you have all the time today. Do it carefully, do it slowly. This is the first time we are doing a group work like this, and I'm making it as a Google Sheet, so I'll explain what I want you to do. You all submit your group works on Google Sheet anyway. So what I want you to do is fill in the Google Sheet, ready on your copy that, put it on your own shared Google Sheet with me and just work it that way. All right, which is what you've been doing anyway. Okay, so let me get to that one right now. What is it? What is the assignment? All right. So the assignment is this. Okay. So first of all, I want to give you a little bit more to chew on. So instead of just having three trees or three trees, I'm having you do 10 trees, but you can use R to help. And I want you to predict, I want you to basically find these things for the first 5 houses in Boston too. So so you can fill this table in now. I advise you to copy this table and make it in a Google Sheet. You can later copy paste back to Google Doc. It is easier to paste things from R onto a Google Sheet. All right. And you can also use Google Sheet to do certain calculations. This kind of thing, simple averages. I can teach you how to use Google Sheet if you don't know. I don't assume students know how to use Google Sheet, but I think most of you do. Like things like averages and sums, you know, type of formula, right? In Google Sheet, it's like Excel. So, but if you need help with that, I strongly advise you to actually do this assignment if you want. Do it on Google Sheets. I don't know why I did it in a Google Doc, honestly. I regretted it. Because you can copy this, paste all this onto a Google Sheet. It will actually help. It's more efficient. So do it on a Google Sheet. Later, instead of having to share a Google Sheet with me, why don't you repaste back onto the Google Doc? But I think work on a Google Sheet. That will help you. All right. So this is the assignment. I want you to look at Boston 2, Boston 2, and that's on Moodle. Use that Boston too. And I think I will let you read the assignment yourself, right? And you can slowly do it. You have all the time until the end of the period today. So let me first of all paste this onto our usual place, which is our class coding page. Okay, so our code, our code. This is the one. Okay. All right. So as I said, I strongly recommend. Now, you can do as much or as little of the computations on R, but honestly, you can even make R code that can automate this, but I don't think it's worth it because I just want you to understand what you're doing. And so I don't think you need to do something like that. All right. So let me go to a new page. All right. That'll be a bit easier to see. Okay. Here we have this. I think you should use Google Sheets, but if you want to use R to compute things, be my guest. Just fill in the cells. It's easier for me to grade that way. All right. And please make sure you follow what I say. When you do your bootstrap trees, please use set seed 1, set seed 2, up to set seed 10, so that you get the same bootstrap tree that I did. If you forget to do that, your tree is going to be different from mine. Your answers are going to be different from mine. So just make sure before you do your resampling to get the indices of what tree you want and things like that, make sure you do set seed 1 before you do any sampling with replacement. All right, so that we get the same bootstrap sample. Why am I? Yeah, you may be thinking, why is Dr. Cole telling us to make a test set? Didn't you say the OOB doesn't have? Yes, I ultimately want you to compare a true test set error versus an OOB error. You see, that's why I'm still asking you to sacrifice and make a test set. All right. So I think the only thing that I have to say is you will actually find it's quite good, the approximation. And see, this is only based on 10 trees. I didn't ask you to do for 500 trees. right? I just want to demonstrate whether you understand how to do this for capital B equals 10, all right? And it's already quite a good approximation of the true test error rate, all right? Test error MSE, sorry.